So thank you. Good morning. My name is Antonio. I'm a PhD student here at TITS, and as you can see from the title, it's vaguely inspired to Star Wars. And I will tell you in a while the reason for why we called it Return of the Features. Okay. So let me start to summarize what we presented last year at the Astroinformatics in Cape Town, where we presented a model for photometric redshift estimation that was based on the mixing of a convolutional neural network and of a mixed, and a mixture density network that was fully probabilistic, so we were predicting PDFs directly from images in a multi-modal way, and it was source independent. But as also Ashish yesterday pointed out in his talk, such a model has two main weaknesses, we can say. In particular, that it tends to become a sort of black box, and that it's really hard to give an interpretation to the features that this model is automatically predicting. So we started to think about the problem of features, and if we consider the features that are classically used in literature, that we will define as classic features, they are basically magnitudes and colors, and they represent a sort of, as it's defined in the literature of the field, a sort of poor man approximation, a broadband approximation of the spectrum of an object. So we say it as our mission that is pointed out here states, can we do better? Is it possible to improve this, finding better feature? And in particular, could it be possible to take the advantages of these two words, methods based on machine interaction and the knowledge that human put in feature extraction and selection? So we considered all the 90 parameters from the Sloan Digital Sky Survey database, so magnitudes in many different ways like PSF, model magnitudes, the Vaucouleurs, and so on, with their errors, and also shape-related parameters like radii, ellipticities, and so on. And we performed a massive combination of these parameters, taking things like differences, pairs, ratios, adding the extinction, so the reddening or not the features. And we ended up in something like 4,520 features. Now, the thing is, if out of this number of features we want to find the possible best combination of 10 features, we would need to do this number of experiments, something like 10 to the 30. Obviously, it's nothing reasonable, and we have to find a more clever solution. And the solution that we found was adopting a forward selection model that basically is meant to build a tree of features in which every branch of the tree represents a possible best set. This was done taking our sample of data that was a sample of quasar from the SDSS, something like 83,000 quasar, and running recursively K and N experiments, taking a sample of 20,000 data for 100 times. And at every run, the best feature or the best features were selected. And then the most probable feature was fixed. Then this was repeated, fixing this first feature and allowing a second feature to be selected. And so on, building the nodes and the branches of the tree until we reached the 10th feature. Clearly, all this required an intensive application of GPU computing because all these experiments were run in parallel. We had to do 100 samples, as I said, per 4,520 features, plus the cross-validation that was a 5-fold cross-validation. And at the end, when we had established the structure, this complicated structure of the tree, we performed random forest experiments with every branch of the tree in order to test them with an independent model. And then how to visualize such a complicated structure and all this interaction between the features? We introduced this diagram that is called a core diagram, and I think it's used in biology typically. That if you look at it at the beginning, it will seem a bit confusing, but you need a while to understand how it works. But basically, every letter represents a feature from this set, and the stripes represent all the connections between the features, with the thickness representing the number of connections between those features. So, yeah, if you take a moment on this slide, then you will understand how it can be useful to directly visualize all the possible connections and relations that appear between the features. And what I want also to point out is that if you look at the features that we found, they also look very strange. It's not easy to say, what do this feature mean? Or anyway, to give an interpretation to them. But I will come back on this in a few minutes. First, let me show you some results. In this plot, I show all the results with every possible subset of the features in the tree. So with every branches, adding them one by one, and you can see that they appear as a single dot. Also, if these are multiple experiments, because the difference between the different subsets of features is so tiny that it's not visible. And this is already an index of great stability of the model. There's not a big difference between the different subsets of features. But what is really important is that from the addition of the fourth feature, they already, in terms of the root mean square error, start to perform as good as the classic ones, all the 10 classic features. And by adding the other features, they completely outperform the classic features. Then when we reach the 10th one, the trend starts to be asymptotic, and therefore this means that it's not useful, at least with this model, adding other features. And here you can see all the different features that we found in different experiments with a bit different data sets, but in particular I'm referring to the experiments with this last set of features. And here you can see the plots of spectroscopic redshift versus the predicted photometric redshift for the classic features, for just the first 4 features that represent the point in which they start to perform as good as this one, all the best 10 features that we identified, and also with the automatic model, the deep convolutional mixture density network that I showed in the first slide, and that we use it as comparison. And from the results, what is really interesting to notice is that the convolutional model is also outperformed by the best 10 features that we found, both with respect to the root mean square error and to the CRPS, that is the error function that we use when predicting not just point estimates, but PDFs, so probability density functions. And this is a very interesting result, because it means that in some way these 10 features are capturing so well the important information that is contained in the data that they are outperforming this massive number of features that is automatically extracted by this model. Now, let me say that this model has still some advantages. There are some reasons to decide which one is better to use with respect to what one needs to do, but still we can discuss later, perhaps, if you are interested in this problem. Now, the thing is how to interpret these strange features. There's something strange that happened at the end, I'm sorry. So we want to give a physical interpretation to these features, try to explain why they appear so strange and what do they mean. So we selected just the the features that were composed by neighboring filters, neighboring magnitudes. And we compared the feature importance given by the random forest calculated beam per beam in redshift with respect to the quasar emission lines that were transferred into the redshift space by this relation. And we found that there is a surprising correspondence between the quasar emission lines and the peaks of feature importance given by the features that we found. And this is just partially true for the classic features that are represented by the gray area in these plots. And this is this can be verified for the colors of the classic features calculated by the PSF magnitudes and for the model magnitudes. And here you can notice it in much more detail. Oh, sorry. For example, this is really striking, and the PSF color is not able at all to capture these lines that correspond to this peak of feature importance. Instead, it's true for the model magnitude, or just partially done for this other peak representing the oxygen line, and so on. So this means that we are able to explain at least part of our features in terms of the processes that are going on in the sources, and to find a physical meaning. And this means also that the model is able to capture this meaning and then extract features that also, if from a human eye at the beginning, are hard to interpret, but this can be done in this way. And therefore, let me conclude saying that we established this model that in the end gives better performance with respect to both using the classic features proposed in the literature, but also respect to automatized model like the convolutional neural network. And it combines in some way the advantages of feature-based model with performances given by a massive selection, because with all that combination of features we increase in some sense the information that we are giving to the machine. The model is highly stable. There's not a big difference respect the performances given by the different branches of the tree, and also the structure of the set of features that we found in the different experiments is pretty similar. There's a common structure, so it means that the model behaves in a very stable way. And it's possible, finally, to give an interpretation for at least for some of the features. We are still working on trying to understand all of them, perhaps, but this is still something open. And then, in the end, let me thank the people that worked with me at this project, so my supervisor Kai Polser, Stefano Cabuoti, and Fabian Giesecke. And I leave you with the message of the little Darth Vader. Thanks.